Hello, everybody. Good afternoon. Welcome to the course. So we have Rupesh here. Rupesh is the lecturer of the course. Let me introduce myself for those of you perhaps don't know me. This is Ali Reza Dehkani. I am AI Technical Program Manager at CIDAR, and I'm leading the Lighthouse project at CIDAR. So every year we have two Lighthouse projects. In the Lighthouse project, actually, we introduced the emerging technologies to the interested CIDAR members and industries in Ireland and so on. This year, we are running two projects. One of them is Graph Convolutional Network, and the second one is AI Digital Twin. In the Graph Convolutional Network, which Rupesh is leading that project, we have, through the course of the project, we have done a lot of interesting activities, including developing educational content, developing technical demonstrators, and so on. So one of the activities of the Lighthouse project is the course. So we have developed this course for you, and during this course, 5 weeks, we are going through to a lot of different aspects of graph convolutional network, a very beautiful and interesting topic in the technology, which is really trend, and a lot of businesses, companies, and so on, they are developing their products around it. So I don't want to talk too much, just I wanted to introduce to you what is the story of this course about. It is 5-week course, twice per week, Monday and Friday. We will meet at 3 p.m. Irish time, 4 p.m. European Central Time. And we have the community page. Rupesh already have invited you. Over there, we can discuss the things, everybody in the course. Rupesh will share extra materials for the reading. And during the course, you please take the opportunity to raise your hand, show any reaction, ask your question in the chat room, and also even open your microphone and ask your question. So that's kind of interactive course. I know Rupesh has done a lot, and he has a lot of interesting materials to teach us. So I will cut it in here and leave it to Rupesh to start the session. I hope you'll enjoy the course, and thank you very much for joining the course. Rupesh, that's for you.
Thank you very much, Aliza, for introducing me. And hello, everyone. Welcome to SEDA Lighthouse Project Season 2, Graph Convolution Networks. And once again, thank you very much for all the industry members, researchers, and students taking part in our brand new course, The Power of Graph Convolution Networks, Master Graph Based Machine Learning. So myself Rupesh, and I will be your instructor for the next 5 weeks, and we have very good interesting topics for the entire course duration with interactive individual tasks and homeworks.
So this is our first week and course one. So let's get started into like graph data and graph convolution networks. So in this content, we'll be discussing a brief about like what's a graph data and what's exactly like graph structure data look like, what is like a node and edges, and what all those examples of graph data, what are the advantages and disadvantages of graph data, and where the graph data is being used. And we'll be jumping into like introduction to neural networks and a slight introduction to graph neural networks and their histories, different types of GCNs, which is better in terms of like a neural network versus a graph neural networks. So where all the graph machine learning applications is being used, and jump into like knowledge graphs and a couple of visualization tools. So like let's start with the graph data. So basically the graph data refers to a data that is structured in a graph structured format. So graph is a collection of nodes, also called as a vertices, and edges, also called as a relationship between the nodes. The graph data is particularly useful for a representation of complex relationships and connection between the different entities. For example, if we take like a social network transportation, or like a recommendation system, or like a chemical bondings, or like any other reactions and everything, we can see all are linked with each other. And these type of has like a very good modeling for our graph structure data and for our graph neural networks. So basically there are like two different types of graph data. So they are like a directional graph and undirected graphs. So what's a directed graph? The directed graph means like they go from one node to another node, but not necessarily they go in a reverse direction. So in other words, like if we have a let's have this example like data graph in the right side. So the node 1 is directly targeted to node 4. So that means like it is a directed graph from node 1 to node 4. But it is we can't do like a reverse from 4 to 1. So it does not accept that kind of relationship here. So likewise, in undirected graph, we don't have like any constraints. Like from one node 4 to node 4, node 1 to node 4 has like a direct connection. And node 2 to node 1, that's a direct connection. Unlike in undirected graph, there is no like strings attached like that. It is like we can go in a reverse direction as well from entire graph. So let's jump into examples of a graph data. So you are seeing like 4 different examples of graph data. So now let's take example of a social network like Facebook. So where each users like Ram, Amir, and Sita, they are all the nodes. So where Ram has a connection between Amir as a friend, and Ram's has a connection between Sita as his wife. So now the wife and the friends are called as edges, and the individual persons are the node. How well they are connected. So let's jump into like another example of movie graph data. So where the nodes are like individual movies and the people, like say, hey, example, like a journey is a movie, that's a node. And people like Tom, Ali, Jack, Rupesh, you are also another node, and how well they are connected. Say, for example, so Tom is acted in a journey. So the acted is edge between the nodes. Unlike the journey is being directed by Tom Cruise. So that's also another edge. That's the relationship between the Tom Cruise and the journey. So these two are like directed graphs. So let's jump into like another example of navigation graph. So let's consider a transport navigation graph data where nodes are like travel destinations, such as like a time, like from one place to another place. An example like Times Square, New York, New Jersey, and Boston. So these are like a node attributes, and they are like places and entities. Where the connections between them are like the distance between them, the traffic, the speed, and the type of like the duration. They're all like edges and relationship between them. Now let's take an example of a chemical relation graph data. So in a chemical relation graph data, the atoms where the individual atoms such as like carbon, hydrogen, sulfur, nitrogen, and oxygen are like nodes, and there are different types of bonds such as like a double covalent bond or like a single covalent bond, or like the or covalent hydrogen bonds. They are all like edges between them. Basically here we can see there's like a completely, there is undirected graph. So there is no relationship like a pointing relationship between from one point to another point, or vice versa, something like that. It's not a, so each and every node has connected with another node, and reverse is easily possible, and you can move from one direction to another direction until the end of the graph. So now jump into our graph database. So graph database is basically like our generally we all know like a database which stores effectively our graph structured data. So in graph database, data are represented in like nodes and vertices, where the nodes represent the each entities and relationships are called as like edges. There are like a popular graph databases like Neo4j, Amazon Neptune, ArangoDB, Microsoft Cosmos with Gremlin API. So these are like like our today's market, like a leading graph database providers. In our course, we'll be using a Neo4j. So what is the like advantages of graph data? Basically, in a graph database, the main important reason is like efficient representation of relationships. The graph databases are designed to effectively represent and handle the representation between entities. This is particularly useful in scenarios where the relationships are crucial part of like data, such as like social network. Each and every like user is very important for them, and for recommendation systems and hierarchical structures. Graph database are very important for complex relationships. Say, for example, like if there is like a one-to-one relationship, that means like in a we took like a last example, like a Facebook graph from Sita is connected with Amir. They have the relationship of friend. That's one-to-one relationship. And here, like in graph, you'll be having one-to-many and many-to-many relationship, and complex hierarchical relationships also is possible. Say for example, like we have like millions of followers for a particular person, so that means like one to many. So these are like a specific kind of informations are stored. So to retrieve this specific type of information, we need to have a database that can handle complex relationships basically. The next important thing is like the complex query and traversal. So as we said earlier, like now we have already have like complex relationship. So how can we retrieve this information from one point to another point, or one to many, or many to many relationship by using the queries? There are like a cipher queries is being used to find like the shortest path between a one node to another node and one connection to another connections. That's the very important concept of graph database. So next important thing is like a natural representation of world scenarios. So many real world scenarios can be easily captured using graphs. Say for example, like we discussed in our previous section, like Facebook as an example, a chemical reaction as an example, and a movie or reviews or a movie like a database as example. And moreover, like this can be used for further like recommendation building processes or recommender engines, whichever is possible, we can do it. Basically, they are of like a flexible and like a schema less in them. Why we say like a schema less or flexible? So basically, why? Because like we can add n number of nodes to a particular or defined nodes. There is no stoppage between them, and there is no particular endpoint. So we can add n number of nodes and edges and relationships. So basically, the graph database is like very easy to add those representations within the specific set of real world entities using a complex queries and complex database arrangement and modeling. That's the main advantages of graph data. Likewise, we do have like a disadvantages as well. Like, so one of the biggest disadvantages is like the cost of graph database. So graph database nowadays, like it's very huge and expensive one. So it is used by only like top tier companies who can afford that much enough of money, something like that. And it comes with like certain strings as well. Say for example, like storage overheads, because like there's like we are increasing the nodes and edges to n number of sizes. That means like we need to expand our storage capability. So it's gonna sit on our head, and like it's gonna drain our entire database and like entire memory resources. Because of this memory resources, it's gonna take us our entire huge set of money which we're gonna put in. That's the complete like strings here. And one important thing is like a limited use case abilities. For example, like so we can't use like some of like a tabular data. So very like specific set of tabular data we can use, and we can convert them into like graph structure data. And there's like a problem with complexity of modeling the data. So basically, like people like who are like well versed in the relationship, they are like the normal relation data. they uh they can't use directly graph database. They should have like graph database. They should have like a basic understanding of like what's the knowledge graphs, and how well it is connected, and how well it is moved from one place to another place, ensuring the relationships are properly represented and the graph structure fits the application needs. And it requires basically like a significant expertise in that domain. Next important thing is like a learning curve. Basically, the graph database and graph neural networks are like a booming concepts right now, and it is like completely like different with traditional relationship database. And it has like a large scope of development as well, and like it requires initial high maintenance cost. So some of the like applications of graph data. So graph data is being applied in like social networks, recommender systems, knowledge graphs, fraud detection, web semantics, telecommunications, urban planning, supply chain management, biological networks, and road networks. Basically, the social networks, they are like a Facebook, Twitter, trends, and everything. A recommendation we have seen like a Netflix, like movie recommender, or Amazon product recommenders, and everything. Knowledge graph building, linking from concepts from entire facts, and fact checking everything or comes in knowledge graphs. And routes and mapping, like Google Maps was being using with like our graph database to map it. In our latest banks, they are using like fraud detections to detect like anomalies in suspicious patterns of payment transactions. And in biological networks, like to find which what diseases and what causes some like biological changes and disease pathways. And semantics, so basically like that's our important concept right now, it's booming on. So it's like a intelligent search and data integration with place with like world web something. And mostly on like a network security platform, for finding like a cyber threats, or like a potential in a pattern finding of if the suspicious activities findings can be easily possible using a graph data with the pre-information of that. So these are like some examples of applications. So now let's jump into our history of neural networks. So history of neural networks date back to 1940s, when when that was we had discovered like basic of artificial neural networks. and and if you know aware in 1970s, a propagation came, and slowly in like 2012 AlexNet came, and slowly we have jumped into like a GPT right now. So if that's the our native neural networks, and if we talk about like graph neural networks, so there was like a boom in like late 2000s, where there was like a paper related on the graph structure complex data were introduced. And later on, the like a famous paper of like graph neural networks, which was released in 2009. And that was like a basic paper, and which gave path to the great improvements in graph neural networks, and how can you use the graph data to form a graph and convolution networks and everything. So in 2016, paper named like autoencoders was published, and subsequently in 2017, the Great Convolution Networks was published. And 2018 gave like three different papers. They're like graph attention networks, graph recurrent neural networks, graph convolutional long short-term memory networks, and graph transformer architecture was released in 2019. So what's a neural network basically? So we all know like a neural network is artificial neural networks. It has it's a part of like a machine learning, where it is functioning based on our human brains, like each and every neurons. So these each and every neurons are linked with like a multiple set of layers and like sub layers within our brains and everything, which sends signals from one point to another point to give a bigger output for us. The same like is being processed using the same technology, and biological technology is used in our machine learning concept of neural networks. So let's jump into building blocks of neural networks. So basic building block of neural network is a neuron, or also it's called as a node. It receives an input, and it processes and produces an output basically. So now in a biological situation, our biological situation knows reacts to the signals, and the signals process those information through a cell body and transmitted through a output of axon. That's in our human cell. That's the process. Likewise here we'll be having the connections and weights. The neurons are connected to each other layers, and each connection between neuron has a weight associated with it. These weights determine the strength of the connection, indicating how much the influence one neuron has on to the next. Likewise, like once we give the input to as an input layer, and process and performs like multiple operation in between using those connected weights and connections. Once these weights and connections are done, there's like a extended activation function is being processed in it. So each neuron has an activation function which introduces a non-linearity into the model. It takes the weighted sum of the inputs and applies a non-linear transformation functions like sigmoid, ReLU, leaky ReLU, and much more, like to do a complex relationship. And furthermore, like we having like forward passes and like back propagations. So in feed forward passes, like the input layer through the hidden layers, and it message is passed to like output layer, and then it is compared and designed with like with the target, and then the error is being computed. Likewise, in back propagation, the process is adjusted using the weights of the connections in a neural network based on computed error in it. This is basically used using a gradient descent optimization algorithm for it. And later on, we'll be like applying this with like different learnings and like learning rates and like different iterations over epochs. We will fine tune it and we'll be getting it. So finally, though they are like basically this set of activation functions are being computed using like within the many hidden layers. The more the hidden layer, our output is going to be like much more refined and like based on like training iterations and epochs. So one of our best example right now we can say is like which is architectures are like RESTnet, Inception, and long short-term memory and GPTs. So these are like a basic examples of like a neural network which is being used. For if you consider like for computer vision, like a CNNs is there, object detections is there. For GPT, it requires like a sequential data as an input format. And for like the computer visions, it requires like yes, image formats and everything. So now let's go on to like a graph neural networks. So basically the graph neural network requires graph data as an input format for it. So graphs are like as I said earlier, like they are represented using the nodes and edges and which interacts with them efficiently from one point to another point. So graph neural networks are like a well-suited task for like complex relationship identifications, say for example, like a recommendation system building or like a social network finding or finding a link prediction or like a link classification or a node classification and a graph level task. It is like easily possible using a graph structured format of data on top of it with the graph neural networks. So let's explain the graph neural networks. As I said earlier, like graph data is like which are like graph formatted data are input for graph neural network. Once this input, which has like a nodes and their connected edges, it is passed to a message passing mechanism. In this mechanism, the graph is being aggregated from its like neighboring informations. So the neighboring nodes and those information are being aggregated here. Once this aggregation is processed, it gets like a new set of like information about aggregated data and how those data are being like locally we can take how it looks like and what to format next and every steps. So once we have the message passing mechanism, the next this aggregated data is passed to a node relationship. So node representation is nothing but like it's a characteristics or attributes of each and every nodes. So each and every node which represents like it's like a feature vector that represents the characteristics or attributes. Basically, these are like a nodes specific information. Say for example, in a social network friend node, like Ram has a friend Amir, and Ram's wife is Sita. So these contains like different set of specific informations here, the friend and wife. So these information are here is like computerized and they are aggregated. And once the aggregation is done, we collect this aggregated sum of data and we collect it and we store it. Likewise, we get this edge representation as well. Once the edge representation is done, we are be doing like a aggregation function. So aggregation function is applied in like applied that combines like multiple like forms of input data from our connected nodes and their connected edges. These are like say for example, they are like a summations of those important feature vectors, and they can be like a mean or like some other computer like sigma values they are being computed. Once the aggregation function is done, now those data are being used as like node functions. A node function is being used like more, it's also called like a non-linear function, which combines the received messages from its own current representation and which adds to the as a output values. So now, like say for example, we discussed regarding like a Facebook network graph from Ram's wife is Sita and Ram's friend is Amir. So we have this combined information is aggregated and then it is passed to aggregation function. We get the feature vectors and feature matrices. And now these feature vectors and matrices are being again fed into like a non-linearity functions and everything. And we'll be getting a combined scores of these functions. That is called like output score here. And that is fed into our graph convolutions, where activation functions like ReLU, sigmoid, or being is applied. And later on, the multiple layers of like our neural networks is being followed here, right? From like our last output is being going to be like an input of next. Likewise, multiple layers of hidden like a network is being done, and thus it's making us like a deep convolution networks of multiple layers of hidden networks. And finally, we'll be getting like aggregated information of each and every nodes as in form of like node labels or like a new set of links or like entire graphs or entire subgraphs level information we'll be getting it. So these informations are being taken and passed and fed into like our front end to do like a recommendation system building or like node classification or like predicting like any diseases and everything is possible from this data. So now let's go to like aggregation function example. So from this aggregation function example, let's take input graph which contains like 1 to 6 nodes and they have the connected edges between them. So now let's take a target node of 4 and see how well it is directly connected to each other. So now the target 4, which is here. So now we can see like how is which are all the nodes directly connected to the target 4. So we can see like a node number 3 is directly connected, node number 5 is directly connected, and node number 6 is directly connected. These information are then fed into like aggregation layer and later on is passed into an aggregation function. Likewise, we can compute the different aggregation functions or different layers and functions for different set of nodes. So if we consider node 3, like a node 1 is directly connected, node 2 is directly connected, and node 4 is directly connected, and later this information is passed into an aggregation function. Likewise, for node 5, 1 is directly connected, 4 is directly connected, and 6 is directly connected. And for node 6, and like node 2 is directly connected, node 4 is directly connected, and node 5 is directly connected. And likewise, is passed into like an aggregation function. So let's explain like what's exactly happening inside an aggregation function. Say as I showed you example, like a node contains like, for example, node contains 1 to 6 different set of nodes. So for each node in the graph, the node's feature vector undergoes a transformation using a learned matrices, and then this transformed feature vector of node neighbors are being aggregated. This is basically done by computing a weighted sum where the weights are determined by the edge weights of the graph. So each and every edges are being computed here, and those weights are being calculated for the softmax functions further. So now we need to compute the softmax function. So softmax function like that ensures the weight will be sum up to maximum of 1, providing like we'll be doing like a normalization for our neighboring nodes and everything. And later it is passed into like aggregation feature vector using a non-linear activation function. So like the best example is to use like a ReLU or leaky ReLU or some other non-linear functions we can use. And then we will be getting a feature vector as an output for our graph convolution layer for a single node. Likewise, we need to follow this same steps for like different set of nodes in our entire graph. And thus, each layer nodes feature vectors are being updated on based on the neighbor's feature And finally, we'll be getting a global structure of a graph that can predict what exactly we want to achieve, and what based on achieve in the sense like if we going to do like a graph level task or sub graph level task or entire mission graph task. So now let's discuss upon what's the difference between a normal neural network and a graph neural network. So in normal neural network, we need to have a data input data should be in like a sequential format without any missing values or anything like that. So in graph neural networks, we need to have a data should be in a graph structure format. So it's like predefined format. We need to follow those formats and everything. So the input should be example of like should have like a nodes and edges, and it should contains like it can contain like a node features or like edge features as well. But unlike in neural networks, it contains like a fixed set of sizes of like a vectors or matrices. So next important thing is like based on the type of task we will be doing like graph neural networks, and there are like a different set of like parameters to consider that. Say for example, like one important parameter is like a node can have like a similar set of properties and attributes that shares within a multiple set of nodes. But like in our neural network, that can be like a bit hindering. Why? Because there'll be like duplicity will be there, and we need to handle those and everything. And next important thing is our aggregation. Here in graph neural networks, each node is being aggregated based on the neighbors connectivity and everything. Here in our neural network, exactly same is done using like a feed forward processing. So a couple of examples of like in graph neural networks are like social networks finding, recommendation system, biological networks, community detection, anomaly detection, pattern finding, semantic analysis, and each and everything. In traditional neural networks, it is used for like a speech recognition, NLP task, computer vision, object detection task, etc., and each and every task is. So handling of data. So graph neural network can handle any type of data, say any type in the sense like they contain like irregular data. But unlike our neural traditional network, they should have like a fixed size of datas, and there should be like no missing values or like no empty, it should be there. Otherwise, it causes a bias in our training module. But in our graph neural network, we don't need to consider this too much of like our incompleteness of our data. Why? Because our entire graph is going to be fit into a data. If one missing point is not there, that means like the connection will not be connected directly to it. So as I said earlier, like aggregation function is completely dependent on the neighbor network, neighbor nodes and everything. If one node is not connected to another node, so that node will not be considered for this type of process, and that is the biggest advantage for graph neural network. Next important thing is like a computational complexity. So graph neural network is dependent on the entire graph structure and the connected patterns in it. And the traditional neural network, it's completely dependent on the input training size and like training dimensions, basically. So what are like advantages and disadvantages of our graph neural network? So in our graph neural network, we can say like effective graph structure data. So GNNs are like specifically designed for like processing data of a graph structured format. So different examples are, as we know, like a social network analysis, chemical bond analysis, or traffic analysis, we can do it. And next important thing is like it captures like local and global dependencies. GNN are capable of capturing both local neighborhood level and entire graph level informations, and allowing them to understand complex relationship within the data. As I said earlier, like we can concentrate either in a small set of a subgraph or entire graph level data we can concentrate, and we can do like a different set of predictions and analysis. Why? Because every graph is connected to another set of nodes. Likewise, from end to end, from top node to like the least node. Next important thing is like a parameter sharing. The sharing parameter across a node enables the graph neural network to generalize the learning in different parts of the graph. and making them more effective for larger graphs. And next is like a hierarchical learning. GNN basically uses like multiple layers of information aggregation, and then it is being suitable for like a further training, and it understands like what level of dependencies it require and in a broader scale. And next important concept is like invariance to node ordering. So GNN are basically invariant to ordering of nodes, meaning that they can process same graph regardless of how nodes are being arranged. If it is like being in like a jumbled format, like a very complex relationship, like which we can't even manage to see in our like a naked eyes, it is easily possible for a graph neural network to visualize them. So of course, we'll in our next coming classes, you're gonna visualize those like very important and like very complex graphs and everything, which is not easily visible in our naked eyes. Say for example, like a millions of nodes is being connected to a single set of node. Say for that's an example of like a Tom Cruise may have be having like a millions of followers. So if we need to visualize those millions of followers, like that's going to be like a crazy amount of stuff which we need to have it. And like there are a couple more like tools to view them as well. In our coming class, we'll be discussing what those tools as well. So we also know that like graph neural networks are like a best for handling like irregular set of data. So the irregular set of data are best suited for like a real world scenarios, like from connections from one point to another point, or like one missing data, or like if there's like a information which is lost between one from one pattern to another pattern, completely different patterns. Our graph neural network can find those like using a like link prediction or node prediction to find the like neighboring weights and everything, and it can match up to it. So likewise, if there's a pros, there should be a cons as well for us. So graph neural networks has like a limited generalization of unseen graph. So GNNs are often designed for specific graph structures encountered during our training processes. They may not generally well to entirely new types of graph known as problem of indicative learning. So we need to make to ensure that the entire graph is being trained and is well aware of what is that from end to end of our data. Otherwise, those missing data, it can find the missing data and pattern finding until it learns completely. So next important thing is like a computation complexity. So GNN are like it is working. It will be very perfect for like large set of graphs, and like they are like computationally very expensive, and it requires like large set of training hours for training, and it requires large set of GPUs and everything. So a couple of companies only uses like a GCN. Say example, Twitter uses a GCN. Pinterest using a pin sage algorithm, that's part of a GCN only. And threads like Instagrams is a new kind of like thread, all very be aware of that. So that also uses like graph convolution networks for that. And next important thing is like and difficulty in handling like dynamic graphs. The handling dynamic graphs where the nodes or edges which changes over time can be challenging for GNN. And, because they need to adapt to the changes of graph structure. And basically this research is ongoing. Say for example, suddenly I might be having like 100 followers. The next day I'll be having like around 40 followers. That's a sudden shortage of like followers drop. So that's going to be like a challenge for GCN. Of course, this is like very small numbers I'm telling. Basically, like for people would have like a millions and more billions of followers. So that's going to be like a very difficult task. And another example will be like finding like semantic analysis. So finding the trend analysis, what's the latest trend. If there's like sudden like a low in trend, the GCN should easily they should adapt to the changes. That's the ongoing research in this field. The next important thing is like a lack of some architectures. Some GNN architectures may struggle to compute like global graph properties, such as like they primarily focused on like local information and additional mechanism. Basically, for in order to like concentrate more in pooling layers, we need to include like a global context of that. So more additional data is like more useful for our GCN. And next important thing is graph neural networks are sensitive to graph structure. The performance of like graph neural network can be very challenging because basically they need to have like a different topologies of data they input graph type and their patterns. They should be like a very unique and very different set as well, which can perform a set of different tasks for each and every like specific use cases. For example, like a pattern finding, community detection, and community analysis. So in these conditions, like a very large set of graphs are like a very useful. If it is a shorter graph, our prediction will be going wrong, kind of. So next important thing is like our exactly like interpretability and explainability of graph neural networks. So this is like a very biggest challenge right now, especially for like a complex and deep architectures, which is under ongoing research. So we need to do like a basic design for this before if we need to jump into like a specific type of architecture. We need to know before well what type of architecture is being used for us and what is being known for us, and before taking into like conclusions and like any decisions. So Pinterest using a pin sage algorithm, so which finds a different set of recommendations. Twitter uses like the same set of like autoencoders and like transformative algorithms, which finds the next nearest neighbor. Likewise, we need to be very clear in order to find what algorithm is being applied. So graph neural network types. So basically, there are like 6 different types of graph neural networks. They are like graph autoencoders, graph recurrent neural networks, graph transformer networks, graph attention networks, graph convolution networks. Let's jump into each and every types and their example use cases. So graph autoencoders. So basically, they are like unsupervised learning on graph structure data. They learn on a compressed representation of a graph for a reconstruction. The main uses for them are like anomaly detection, network visualizations. The graph convolution networks, which uses the aggregation mechanism from its neighboring nodes, and they are used for like a node classification purposes, graph generations, and the famous applications are like community detection, recommendation system development, and node classification. Graph attention networks where the each weights contributed using attention mechanism. It's being followed and it's computed within the like entire graphs and everything. And they are used for the node classification, link prediction, knowledge graph building, and community detection. Basically, these graph attention networks are again being used for like a graph classification. The complete topology of graph can be defined using graph attention networks, and finding the graph level, entire graph level recommendation systems we can build using graph attention networks. So graph recurrent neural networks. The graph recurrent neural networks uses a graph in a sequence of node visits. So basically, they are used for node classification and graph generation and link predictions. So next important concept is graph convolutional LSTM networks. So graph convolutional LSTM networks, which combines the graph convolution with long short-term memory. So once it combines like
Hello, Devon speaking.
yeah. Hello. Sorry. So graph convolution LSTM, which combines the graph convolution on top of it with like long short-term memories. So they are effective for modeling long-term dependencies in a graph data. And they are used for like a link prediction tasks, the graph generation task, and node classification task. So next, finally, the graph transformer networks. So graph transformer network utilizes the transformer architecture for processing a graph structure data. They are used for various domains, originally like developed using for NLP tasks, semantic search, keyword searching, like figuring out like which is like a sentence completion task as well. and they are basically for a speech recognition, and one part is being used for a computer vision as well, using a vision transformers. So graph ML applications. So basically the graph ML applications is broadly classified into 4 different types. They are graph level predictions, node level prediction, edge level prediction, and subgraph level prediction. So graph level prediction involves predicting the properties of entire graph rather than individual nodes or edges. In a node level prediction, which involves the predicting of a specific category of a node or predicting its degree of centrality. And in a edge level prediction, which involves in a task in a presence between for example, a link between a two nodes or a prediction types of relationship between them, we can find using edge level task. A subgraph level task, also called a community task. So where the entire subgraph is being considered, and it is predicting the existence of certain patterns or motifs or any different set of graphs in it. So these are all the 4 different types of graph level applications and their tasks. So if we consider graph ML applications graph level prediction ML task, it requires recommendation system building, network analysis, link prediction, graph classification, graph generation task, and graph regression task. So for specific set of node level tasks, so it is used for node classification, the node prediction, the node level recommendation system development, the node level fraud detection, the node level content recommendation system, the node level semantic analysis, sentiment analysis, and anomaly detection as well for a node level task. If we consider edge level, so it is done using entire edge of a graph. For example, a edge level link prediction, edge level anomaly detection, edge level fraud detection, edge level recommendation system development, edge level analysis of semantic search, and edge level analysis of traffic predictions. What's the distance from one time to another time, we can easily predict using edge level graphs. So if we consider entire subgraph level ML task, so the entire graph or subgraph is being considered. So we can do a knowledge mining, pattern finding, drug discovery, protein mechanism, and social network analysis, image processing, graph classification, and an entire network classification, and we can generate entire graph as well. So these are set of graph ML applications which is being currently used in our market right now. So knowledge graph. So knowledge graph is very important terminology as well. So a knowledge graph is a structured representation of a knowledge that captures the relationship between the entities. Say, for example, in a particular domain, it is a way to organize information in a graph format where nodes represent the entities and edges represent the relationship between them. So these are a basic characteristics of a knowledge graph. So they are based on nodes, they are entities, and they are based on edges, they are which captures the relationship, the node properties, node edge properties, their semantics, and their scalability. These are a very important concepts of our knowledge graph building. So we can also find a way what is a difference between a normal graph and a knowledge graph. In a normal graph, it is it's a mathematical representation of connected nodes and edges. But in knowledge graph, it finds a specific set of relationship in a specific domain. So that's the only difference between the normal graph and the knowledge graph. Likewise, it is being differentiated between the edges, the nodes, their dialects, semantics, attributes, and scalability. In normal graph, it is used in a various types of field and various types of sizes and the complexity. But in a knowledge graph, it is used focused only on small set of graphs and small set of like representations and properties. It's very specific to the specific use cases. So for example, like knowledge graphs can be used for search engines or specific set of search engines, and normal graphs can be used for like a recommender, the broader scale recommender system development. This knowledge graphs can be used for like a small set of semantic webs or like a NLP integrations or like other AIML recommender integrations. Unlike the normal graph, which is used in a broader scale of network analysis, and like a broader scale of like semantic analysis and everything. That's the difference between a normal graph and a knowledge graph. So popular visualization tools for like graph data. So they are like Gilpy is there, Neo4j, Bloom is there, NetworkX is like a Python library is there, OpenGL is a Python library is there. These are all like set of libraries and tools used for like graph visualization purposes. So we'll be discussing a brief in our next class, like how can we build our nodes and edges. So in our next class, we'll be building the entire nodes and edges from the scratch. We'll be jumping into like a Python, and we'll be jumping into like a cipher query languages and everything. So I request you to download a Neo4j desktop for the next class. So for more information, I'll be like putting messages in our community here, in our SEDAR community, and I'll be showing you like a steps to do installations and everything. So if you have any questions, I'm open to discuss right now.
I have a question.
Yeah.
So thank you for the presentation. I had a question regarding the data completion specifically for graph neural networks. I believe, if I understand correctly, you said that it's not really a major problem if there's like missing data or something specifically for graph neural networks.
Exactly. Yeah. So yeah.
So are we
yeah.
not losing out on any important say relationship between two entities if there's a missing information?
So one important thing is like if one node is connected to another node, then it is like very important. Here we'll be losing information, but we can find this using like a degree centrality. How well one node is connected with another node based on the shared neighbors, we can find it. So that's one important point here. We can utilize the graph neural networks when compared to normal neural networks. So we can find those like shared neighbors and closeness of those shared neighbors. Yeah.
I see. Okay. And also a very small question. When you talk about neural networks and you say that, more the number of layers, better would be the result. Is it always the case that with an increasing number of layers, the result will definitely get better? Or is there like a cutoff or something?
No, it's completely based on a specific set of use cases for us, basically. So in our use case, like that means like if you do like too much training also, like it'll be like overfitting, it will be. So the specific set of our target, like the use case, based on that, we need to like do like multiple set of trial and errors, and we need to find it.
All right. Okay, got it. Thank you.
Yeah.
Hi, hello.
Hi.
Sorry for maybe the dumb question, but I lost some part of the presentation due to connectivity issues. I was wondering if you may maybe repeat and elaborate more about the difference between the two types of graphs. Thanks.
Exactly. Yeah. So knowledge graph means like which captures the information of a particular domain, and basically it's a way how we organize our graph format, whether like the node representations, the entity representations, or like edge representation. It's completely based on specific like set of domains, domain only. So that's the main catch here. And comparing with them, like for example, like we consider like a movie graph. That's a knowledge graph as well, because we are considering only about the movies, and the node represent each movies, actors and directors, and the edge represents the who acted in it, and how many people have acted in it, and that information. So here, like attributes in the sense like what's the movie name, that is the main attribute here. So how, like here important thing is like semantics. So knowledge graphs are designed to capture the semantic meaning. That means like the relationship between the entities are just arbitrary connections, but meaningful contexts are also being provided here. That's the main important focus here. And also the scalability. So knowledge graphs can scale from small, and they are like they can focus up to large scale comprehensive like information. But in our normal graph, like our graph scalability, like it requires like a large set of graph at the beginning itself. That's the important difference here. And knowledge graphs, we can use it for like search engines here, like providing like question and answers immediately here, for like chat applications. And we can use the knowledge graph for like semantic webs, which understand like purpose and process of the specific context. And in a shorter form of recommendation systems, we can use it knowledge graph.
That was very useful. Thanks.
Yeah.